Hi, everyone, and welcome to Half Day Wednesday. My goal for today is to compare and contrast lenses and mirrors. Make sure you've got all the notes that you need in order to succeed this week and catch us up on anything you might have missed. So, let's sum up everything we've done so far in this unit. We've worked on lenses, which use refraction to bend light as it goes through a prism. And those come in two shapes, convex and concave. Obviously, they technically come in lots more shapes, but those are the two we're going to deal with because they're the easiest mathematically and they have predictable ray diagrams. Whereas mirrors use reflection to bend light, and we're also going to deal with two shapes. We'll do concave and convex. So in your notes, if you don't have definitions for convex versus concave, convex means that the shape bends outward. Concave means the shape bends inward. And you just want to be careful on mirrors that you notice which side is the mirrored side and which side is the side an object can be on. So with this concave mirror, this is the silvered side in the back, and your object would be to the left of it. Okay? Now, convex and concave refer to the shapes of your object. But you will also hear words converging and diverging, and those refer to what this object does to light. We tend to deal with parallel rays of light, and one thing to note is both for lenses and for mirrors, rays of light that go parallel and hit the vertex of your object are not deterred from their original path. For mirrors, they reflect exactly backward from which they came. And for lenses, they go straight through the vertex of your object, undeterred. Rays that come in parallel and are slightly off, however, are slightly above or below the principal axis, are going to show behavior that's typical of your mirror or lens. What I mean by that is this will show if a lens is converging, meaning it takes a parallel ray and sends it towards a focal point, or diverging, meaning it takes the ray and sends it away from a virtual focal point. When we do ray diagrams, this is going to be called ray 1. Ray 1 goes parallel into your mirror and either converges towards a focal point or diverges away from a focal point. In this case, my focal point is back here. It's a virtual focal point. And my ray, these dotted lines, mean that the ray doesn't actually make it back behind the mirror, right? Because the mirror surface is in the way. I mean, the wall would be right here. There's no actual light back here. So wherever you see the dotted lines, those indicate virtual rays. Okay? So a good picture to have in the back of your head is that lenses and mirrors both cause converging and diverging behavior, but one uses refraction so that light reaches the other side, and the other uses reflection. Now, that means when we go draw our ray diagrams, we can just use these pictures one for one. So I'm going to do lenses first. And I'm only going to show you one for lenses, and I'll show you one for mirrors. So when we draw ray diagrams for lenses, and let's do this for a converging lens. Let's say I'm doing a ray diagram for a flower. Ray 1, which I drew in red before, goes parallel into the principal axis and out through the focal point. Wow, so much easier to draw by hand than doing it on the computer, guys. Ray 2 for lenses goes straight through the vertex. Anything that goes straight through the vertex doesn't get bent. So if I take a blue ray of light from the top of my flower over here and go straight through the vertex, I see these two rays actually meet. We call this a real image, where ray 1 and ray 2 actually meet. That gives a real image. And hint, guys, real images are always inverted. To determine if this is larger, smaller, or the same size, remember that this light left from the top of the flower, so this must be the top of the flower, and the roots stay on the principal axis. So this image is just slightly larger than the original. So for my dears that are having trouble with this classifying images, if the images have rays that actually meet up, that's real. And it's always inverted if it's real. To determine larger, smaller, or the same size, we're comparing the size of your image, this is my image flower, to my object flower. Okay. Now, for mirrors, that looks super duper similar. So I'm going to show you how to do ray diagrams for mirrors, and then we'll compare. Rays for mirrors are still going to have two rays. And how about we do this as a diverging mirror this time? And let's say we're dealing with a house. Okay? For a mirror, the center of curvature is referring to the center of this circle. Imagine I drew this out as a big old circle. So the center of curvature is over here. And the focal point is twice. There's two focal points per one center, one radius of curvature. So let's draw the rays. Ray 1 goes parallel in. Now, it can either go towards the focal point if it's converging, or diverge away from the focal point. And since this is a diverging mirror, my ray actually goes back here, ray 1. Ray 2 leaves the top of the object and goes towards the center of curvature. Now, it doesn't actually meet the center of curvature, and why that is the mirror's in the way. The ray goes towards the center of curvature, hits perpendicularly to the mirror surface, and then bounces right back off from where it came. And notice that my real rays, ray 1 and ray 2, don't meet up in real life. Our brain only thinks that they've come from back here. Since these are my dotted lines, that must be virtual image. This is upright because the top of the house was where that intersection was. But the base of the house is still on the principal axis. So this is a virtual, upright, smaller image. Now, I like using ray diagrams to figure out my types of images because that means I have very little to memorize, and I am not a memorizey person. If I can draw this out, a ray that goes parallel in and either away from a focal point or parallel in, all right, there, parallel in, and towards a focal point, that means I have a lot less to remember. So, when I'm trying to classify images, I basically have three tools. I can draw ray diagrams and use that to classify the images that are formed. I can memorize them, but guys, that brute force memorization is tricky. So here's the thing that might help. The other method you could use for determining the images is just brute force memorize it. Now, for some people, this is really overwhelming. That's why we came up with all these other ways to get the images. But keep in mind that any diverging device, so that's a convex mirror or a concave lens, always makes the same type of image. No matter where you put an object in front of it, it always makes a virtual upright, smaller image. These devices then are good for increasing the field of view. So your side view mirror increases the field of view by making all the little cars seem smaller. The security camera at a store security mirror at a store does the same thing. And so does a GoPro lens on a camera. It can fit a larger field of view by making all the objects look smaller. Where it gets tricky is your converging devices. This is your convex lens or your concave mirror. Because if you're far enough away from the object, you get a real image, but putting an object close to the device makes a virtual image. So the pattern here is it goes from real to none to virtual. Real is always inverted, virtual is always upright. But when you're on top of the focal point, no image occurs because the principal rays are parallel to each other. You're not making a distinct image of light. When you're farther than the center of curvature, it's smaller and gets larger the closer you are to the focal point. When the object is far from the focal point, the image is small. The closer the object is brought to the focal point, the larger the image is, until the image disappears entirely when it's on the focal point because the rays are parallel. Bringing it past the focal point makes a virtual, larger image, but still, the farther you get from the focal point, the smaller the image is. And a lot of you guys got tricked on this in the homework, so I'll say it one more time. For a converging device, the closer you are to the focal point, the larger it is, or the larger the image is. This picture is another way to imagine it. So if you have an object that's farther than the focal point, you have real. On the focal point, you have no image, and closer you have a virtual image. For magnification, the farther out you are, the farther away from C you are, the smaller your image appears. And the closer you are to your focal point, the larger the image appears, balancing out to make a same size image at C. So this graph could be used as another way to help memorize, especially if this chart seems like something you would not be into memorizing. But hey, at least your convex images are easy. They're always virtual, upright, and smaller. So that's not too much of a stretch for memorizing. So to recap, in order to classify the images that come from mirrors and lenses, I could either brute force memorize it, which you totally can. Some people are going to be like, yes, I will memorize this. We're doing open notes assessments anyways. Right. We could draw ray diagrams. That way I don't have to memorize it. I just have to learn how to draw them. Or 3, math. I like the math. So we'll work on this on Thursday as well. But there are 4 main equations. And since we're going to practice this in quizzes in just a sec, I will point out that I'm not going to give you a ton of assessments today in quizzes. However, be prepared when we do this on the assessment with a calculator and things so we can actually get these done. What I'm going to review today is how we use these equations to classify images, because that's the point of these equations, is by solving these 4 equations, I want to be able to use them to classify classify images. So let's say I get to the end of a problem and I've gone through my problem and my final number is magnification is equal to positive 0.5. Great, but what's that even mean? Okay, so here's how we do it. The sign of magnification tells you that this is upright. The sign of your magnification, if it's positive, tells you that this is upright. But the number itself tells you the size. So this is telling me it's half the size of the original object. So this is telling me that my image is half the size of my object. It is smaller. And hey guys, since it's upright, that automatically means virtual. This is a virtual, upright, smaller image, and I don't even have to draw any pesky ray diagrams or memorize anything. Right? Let's do another one. Example 2. Let's say that m, and you guys had trouble on this on the homework, so I'm going to point this out. Let's say m is -3. Okay? That negative means the image is inverted. An inverted image is like this one, where the image and object are upside down from each other. Inverted is just the physicsy way of saying upside down. And hey, since all inverted images are automatically real, notice those light rays literally intersecting each other right there. Boink. Those two go together. But the 3, the magnitude of this number, is the magnification. This says my image is 3 times larger than my object. Other numbers have similar positive and negative traits that you should keep in mind. These two, the thing they have in common is focal point is positive because these are both converging. Whereas my other guys, my 2 diverging devices, where it goes away from a focal point, that means f is negative, diverging. And that f positive and f negative, that is for whenever you see an object that's convex lens or concave mirror, as long as it's this shape, f is positive no matter what the image is doing. Okay? So f plus positive means that this is a converging device. F negative means it's a diverging device. Similarly, if di is positive, that means it's a real image. If di is negative, that means it's a virtual image. So those are our 3 methods. So for converging and diverging devices, you can either memorize all the images that are formed, you can draw the ray diagrams and classify there, or you can use mathematics, which we'll practice more on Thursday. So what I'd like you to do is keep your notes out, keep out a calculator, let's try this quizzes, and email with any questions. All right, guys, enjoy your half day. Best of luck.